Good morning, everybody. We're in Chapter 2 in Pre-Calc. This unit covers polynomials, power functions, and rational functions. Our first lesson is all about quadratics, and it's pretty much a general review from things you've seen in Algebra 2. So starting off here, we've got the definition of a polynomial in X, and it looks like this big, scary formula right here. Excuse me. But if you look at it carefully, you can see that we're starting off with some power n, and this a sub n is associated with that power on the x variable. So if this was a fourth degree term, then our next term down would be a third degree term, because 4 minus 1 is 3, and so on and so forth, until we got to a quadratic term, a linear term, and then a constant term. So it's not as scary as it seems. We also have review here for the definition of average rate of change. Now we know average rate of change is just the rise over the run. It's the slope. It's the change in the y's divided by the change in the x's, and you've seen that in this format and in the y sub 2 format. In science, you see delta y over delta x. We know rise over run, and also we know that the slope is the velocity. So average velocity or average rate of change. So all kinds of terminology we can use for the rate of change. Not on your notes, but a few of these. We have general form on your notes. We have slope-intercept form on your notes. And then my personal favorite is point slope form, because as we move into calculus, you're going to want to use this formula for writing equations of lines. So we're going to jump right in. I know this isn't on your notes, but it is a helpful reminder for a zero function, has no degree, that's just a term, a constant function, a linear function, and a quadratic function. And you can see I'm getting the degree from the power on the x. So if I have just a term, that's like x to the 0 power, y equals 4 or y equals -2. In this example, we're going to look at naming, identifying polynomial functions. So right from the very beginning, that a sub n, x to the n power. You can see here, I do have a polynomial. Its highest degree term is a fourth degree polynomial, and the leading coefficient is -9. Is this a polynomial? Yes, it follows the format. In the second one, you've got a square root function. That is not a polynomial. Its degree for a square root is the 1/2 power, because we know the square root of x can be rewritten as x to the 1/2 power. It has no leading coefficient. It's not a polynomial because it has a fraction for the degree. In letter C, our degree is -3 and our coefficient is 8. Now if you think about that leading coefficient, that leading term, we have division by a variable. This is not a polynomial, because we're dividing by the variable, not multiplying by the variable. And then this last one, the highest degree term is cubed, so it's a cubic polynomial with the leading coefficient -5. And even though my constant is a fraction, it still is a polynomial. There's no dividing on any variable, just a fraction, a dividing of a constant. In example 2, we want to be able to write an equation in slope-intercept form. So that's our famous y equals mx plus b. Now, what do you notice about this? I'm hoping you notice you have the b value here. This is my b value because my ordered pair is 0, 3, and 3 is the b value sitting on the y-axis. So the only thing we don't have is the slope, but we could find the slope So let's find the slope first by using the change in the y divided by the change in the x. And that's going to give us a negative because the bottom's negative 6/4, or negative 1.5. So we need a point and we need a slope. Our slope is negative 3/2. And our b value is 3. So this one was a fairly simple one. In example 3, we're going to look at writing slope-intercept form. Whoop, that's wrong. That's supposed to say point-slope form on your notes. So let's change that on our slide here. Your notes say point-slope form. So in this case, we need the slope, which is y2 minus y1 divided by x2 minus x1. And people ask me, students ask me, why did I start with the 7? Because I could. You could start with this y and say negative 3 minus 7, as long as you keep it uniform, and then 3 minus 5 on the bottom. So here we have 10/2, or our slope is 5. Now, same thing here. You could have two different equations. If I use the point 5,7, I'm going to use this point first. I could say y minus 7 is the slope times x minus 5. Or if you didn't like that one, we could use this point. And again, that's just a matter of preference. So two correct answers here. And that would look like y plus 3 equals the slope times x minus 3. So in either case, both of these are correct. They're both point slope form, and you're good to go. So quadratic functions have a degree of 2, and the shape of the graph is called a parabola. And we have two really good formats to write quadratic functions. We can write them in standard form, or we can write them in vertex form. Just depends on what you need, which format you're going to look for. And then the rest of the characteristics, we can have HK. We can also have the opposite of B over 2A, and then substitute that answer back into the equation to find the y value opposite B over 2A. And this is also another form for the vertex. Your axis of symmetry can either be x equals h, or it can also be x equals the opposite of B over 2A. Your parabola opens upward if the leading coefficient is positive, and downward if the leading coefficient is negative. We call this concave up and concave down. And your y-intercept is the constant when you substitute 0. You can have your x-intercepts using the quadratic formula. You can have your x-intercept by setting the equation equal to 0 and factoring, or completing the square and using the square root method. So like I said, this is pretty much a general review of things you know from Algebra 2. Remember, when you're factoring or expanding a binomial, you want to know the trick for expanding binomials, and I'm going to do this wrong on purpose. X plus a squared is not x squared plus a squared. So don't get into that trap. Remember that you have a middle term when you're expanding binomials, because you have distributive property twice. You need to multiply x times both terms and a times both terms. And most of us call that the FOIL technique. But if you know the pattern, you know that you're just doubling the product of the outside and inside. So if you think about it, you can square the first term and square the last term, but don't forget the middle term. If you multiply a times x and you take twice that, that's the middle term that often gets left behind. Okay, so same thing with the difference of a binomial squared. It's going to be x squared and then minus 2ax's. But the last term is positive because a negative times a negative is a positive. And then our last thing we need to review is how do you complete the square? So oftentimes I like to think about the physical model of a square. If I have a square that I don't know the length of it or the height of it, but I know it's a square, I know the area is x squared. And let's say we had some little blocks. These are like algebra tiles. If you had 2 blocks here and 3 blocks here, do you see the idea that you can complete the square by knowing how many missing items are here? So I have, I need one more block. If I have the length here is x plus 3, and the length here is x plus 3, because I'm just saying this is 1 unit wide and this is 1 unit wide, then this part in yellow, this is the part that completes the square, this piece here. I need 9 little single 1 by 1 blocks to have an x plus 3 by x plus 3 square feature, and it actually creates a physical model of a square. So that binomial squared, you can see how I have 2 3x's. I have 2 of those. So when we complete the square algebraically, you first learn if the a value or your leading coefficient is 1, you can isolate the constant as a first step. In other words, you can pull out whatever number is over here, our constant, we can isolate that constant and make a spot to complete the square. We're looking for those little number cubes, the 9 yellow number cubes in that case. The second thing you can do is you can find half of the middle term. Let me back up here and change my pen to blue. So we can find half of the middle term. The middle term is b. If you cut it in half and square that, that's going to give you the value for in here, right? The value for completing the square. I'm going to say completing the square. The value that goes in the box is half of the middle term. Then you're going to add this value to create the perfect square, and you're going to subtract that value from the c to make a 0. So add the value to the trinomial. That's where the box is. And then subtract that value from c. And that's going to give you a different constant. I'm going to call it k. And finally, after you're done, then you can factor and simplify. And what that does for us is that gives us vertex form. So we had a out in the front, which was 1, and it's going to give us vertex form where you have an H and a K. That's your vertex. Okay? We'll do a few of those in a minute. In example 4, we're going to use the standard form to find the vertex form and the axis of symmetry, but we're going to do it with the formula that we knew from Algebra 2, the opposite b over 2a, and then we're going to substitute that back in to find the y value, the opposite of b over 2a. Okay, this one is going to give me my h value, and this one's going to give me my k value. So in our polynomial here, our opposite of b, our b is -8, and divided by 2 times a, our a is 2. So this is 8 divided by 4, which makes 2 the axis of symmetry. X equals 2 is our axis of symmetry. And then we want to find our k value by substituting that back in. So if we substitute f of 2, this is our h value, into the function 2x squared minus 8 times x plus 11, that's going to give us 4 times 2, which is 8 minus 16 plus 11. So the y value of the vertex is 3. This is our k value. This is one way to find vertex form. So in vertex form, we have our a value up here. A is 2 because it's the coefficient of the highest powered term, 2, and it's x minus h. H is 2, quantity squared, plus k. K is 3. Vertex form, using the opposite b over 2a and then substituting that back in. So you have the opportunity to get vertex form that way, or we can get vertex form using completing the square. Now this one is a more pre-calc level because my a value is 2, and I need to pull the 2 out in front of the factors. So 2 leaves an x squared here, and 2 out of the 4 leaves a 2 on the inside with the 2x. And then we're going to have a constant we're putting in there. We're moving the -1 outside, and then, like I said, we'll have to subtract that number in the box. So these are the same numbers. If we add it and subtract it, we haven't changed the equation at all. We're keeping that balanced. Okay? So the procedure to complete the square says, complete the square, take half of the b term and square that. Now what's our b term? 2. So we want to take half of 2, which is 1, and square that. Well, 1 squared is 1. So we're going to add 1 inside here. Okay, here comes the pre-calc level. Now we added 1 inside, but do you see this 2, how it's a factor? What did we really add inside on this portion of the polynomial? We added a 2 inside there. So to keep it balanced, we need to subtract the same value. We have to subtract 2 to keep a balanced figure. And then we have vertex form, because this is the completed square, which was 1. This is 2 times the quantity x plus 1 squared, and then minus 3. Okay, so we used completing the square to describe the graph, and now we want to analyze the function completely. So to analyze, you would want to solve it, graph it. Let's see if we have a piece of graph paper here. Yeah. So what do we know? We know that the vertex was at -1, -3, and it had an a value of 2. We also know in standard form, -1 was the y-intercept when you plug in 0. So we know that point, and we know that point. And we also know that the axis of symmetry goes through the vertex. So if we reflect this point across the axis of symmetry, we pretty much know the shape of the graph, right? So we have the shape of the graph. And the x-intercepts are what we're looking for. We need to know the zeros. We need to know that one and that one. So we're going to go look for those two. Now you could do this exactly or with a calculator. So I'm just going to jump to our quadratic formula, if you like, and do opposite b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. And that turns out to be 16 plus 8. 16 plus 8 is 24 divided by 4. And if we just want the exact answer, excuse me, been talking too much today. Our exact answer, we can take 24 and think of that as 4 times 6. The square root of 4 is 2. And then you can factor out a 2 from this term, and this term, and know what our zeros are. -2 plus or minus the square root of 6 divided by 2. So these are our zeros or roots of the quadratic. And you can either label them independently. This is a little messy. Or you can take your calculator out and find out that this one is -2.225 and this one is positive 0.225. So I have 0.2250, which is this one right here, and then -2.225, which is the one on the left. Okay, so solving quadratics. And quadratics are great for looking at vertical motion, rockets in the air, footballs in the air, golf balls in the air, that sort of stuff. And we like to use the position function. The position function is -1/2, because think about it. If something goes up, it has to come down. So it's negative because gravity is pulling it back to the ground. So -1/2 times the gravitational constant squared times time squared, plus the initial velocity times time, plus the initial height, s sub 0. So s sub 0 is the initial height, and v sub 0 is the initial vertical velocity. And then the gravity, that depends on whether your problem is written in feet or whether it's written in meters. So if it's written in feet, your gravity is pulling you back at 32 feet per second. But if your problem is in meters, gravity's pulling you back at 9.8 meters per second. Okay? For all you physics people out there. And then here's one, our last one. Now we have 2 more. Okay, this is a long lesson. So here, the Surfside Little League uses a baseball pitching machine. It helps train players to catch a high fly ball. It throws baseballs straight up with an initial velocity, there it is, initial velocity, 36 feet per second. From a height, this is my initial height, of 4.5 feet. we want to find an equation that models the height of the ball t seconds after it's thrown. So since we're talking about feet, our gravitational constant is 32 t squared plus initial velocity times time plus initial height. And if you simplified that, your equation that models the path of that ball on the pitching machine is going to be negative 16 t squared plus 36t plus 4.5. And we want to know what the maximum height of the baseball will reach. So I got to go to part C. We should have done part C first. Part C says how many seconds will it take to reach the height? So if you think about this path of that ball, starting here at 4.5, and the maximum height is going to happen at that axis of symmetry, and that is the opposite of B divided by 2A. Well, our B value was the velocity, and our A value was the negative 16. So on my calculator, I'm getting 1.125 seconds. So now I can use that to go back to B, and the maximum height of the ball is going to be the position at 1.125. So using your calculator, you want to plug in that time for the axis of symmetry into your equation that models the behavior or the height of the ball at any time and I got the maximum height was 24 3/4 feet. You can verify that with me using your calculator. So how much time will the ball spend in the air? Well, that would be where the ball hits the ground. So when is this time over here? And that would be the x-intercept is when the ball hits the ground. And using my calculator to find that when is the s of t equal to 0 feature, that's called the 0 feature on your calculator, I got about 2.4 seconds for when the ball hits the ground. Letter E, determine the vertical velocity when the ball hits the ground. Well, on the set of notes it said velocity was negative gravity times time plus initial velocity. And our problem was in feet. So our gravity is pulling us back at 32 feet and the initial velocity was 36. And we found it would hit the ground at about 2.369 seconds. So using your calculator again, we're going to substitute this expression, and I get about 40 feet per second, which makes sense. It's speeding up as it's heading toward the ground. So the velocity at 2.369, speeding up in a negative direction, isn't it? 369. So the velocity at impact is negative 39, or about negative 40 feet per second. And then one of the key things we need to be able to do when we leave pre-calc is read position time graphs. And we've got this position time graph. It shows the distance an object travels from 0 to 150. That should be 150 minutes. And when is the particle at rest? So you can tell here that your object is traveled from 0 to 15 miles, and it took the vehicle 30 minutes to go from 0 to 15 miles. But then in between 30 minutes and 50 minutes, it didn't travel any distance at all. It stayed at 15 miles. So in between 30 and 50 minutes, the object or the car is at rest. It's also at rest between 60 and 80. And between 110 and 120. And all of these units are in minutes for our time. Now, when is the particle moving left? So the particle starts, or vehicle, whatever, starts at the origin, starts at home, travels 15 miles, doesn't travel, travels another, where'd they go to? 35, up to 35 miles, doesn't travel. Now what's happening? They've reversed their position. They're going back. So when the particle is moving left, it's moving right here and then moving left between 80 and 110 minutes. And then again, back home, back to the origin, moving left from 120 to 150 minutes. So when does the particle change directions? Well, it changes directions right there. And I don't know, you wouldn't really say it changed directions right there, but it changed directions at 80 minutes. Whoop, not 800 minutes. 80 minutes. Particle changed directions. Turned around, went back home. So position time graph and velocity time graph. Velocity is like the directed speed, whether it's positive or negative. So when is the particle at rest? So velocity is when we have at rest, velocity would be 0. So right in here, between 30 and 50, between 30 and 50 minutes, between 60 and 80 minutes. I'm going to put intervals here to save space. And then between 110 and 120 minutes. The units are minutes. When is the particle moving left? Well, velocity is positive when it's moving right, and velocity is negative when it's moving left. So that would occur at 80 to 110 minutes and 120 to 150 minutes. Are you seeing a connection? And when does the particle change directions? Well, moving right, stopped, moving right, stopped, moving left. So at 80 minutes, the particle changed directions. Then to sum that up, if we looked at the two examples, what similarities do you notice between the graphs? In other words, how do they relate to each other, or how are they connected? Just to save time, I'm looking at 34 minutes here. In figure B, do you see that this represents the slope or the velocity? Represents the velocity or the slope of the graph. In figure A, for instance, let's go back and look. If you see this is at 30, we went, what, 15? So at 30 minutes, we've gone 15 miles. and 0, 0. So our rise over run is 15 divided by 30, which is 1/2. And if you look at velocity, it's right there at 1/2, isn't it? So the velocity's constant, 1/2 on that first interval. And in figure B, the time is 0 from 0 to 30. It's the slope of A. Let's look at it. Whoop. Figure B, see how the velocity is constant? So from 0 to 30, the velocity is in miles per minute, and it's constant there. So in figure B, on the time from 0 to 30, the slope of A, which was rise over run, was in miles per minute, is the velocity of the B graph. So the rise over run was 1/2. That was the slope on the A graph, and it was the velocity, a constant straight line on the B graph. So here we are, ready to move on in Unit 2. See you next time.